Hello developers, let's start developing. Today we're gonna take on day 11 of the 2024 Advent of Code. And it seems like today's task is gonna be a tricky one. It's one of those that sounds simple, but the complexity is kinda hidden. So I think that we might do a few false starts and then we're eventually gonna get it done as it is. So, for example, we have a line of numbers, stones, and each of them have a certain value, a number on them. And we have a few rules of how those numbers change. So, the first rule, if it has a 0, then it becomes a 1. If it has a number that has an even number of digits, we basically split it in two. First half goes on one stone, the second half goes on two stones. Otherwise, the value gets replaced by the value multiplied by 2024. Yeah. So that's all there is. And we need to run this through 25 steps of simulation, and I have a feeling that for the second part we will need to run it through something like 25 million steps of simulation. So we have this, and that's the starting position, and then we have a step or a blink as it's called here. So the 0 becomes 1, the 1 becomes 2024, the 10 becomes a 1 and a 0 stone, the 999 becomes a 2 9 stones, and a 999 becomes 202197876. That's that. So for this, if we start this, we will have that. So if we start with these two, after blinking 25 times, we will have 55,000 stones. Yeah, the number just keeps increasing, and the number can potentially increase up to the double of the number. So if we start with 2 stones, let's get a calculator. If we start with 2 stones, we can get up to something like 33 million stones. If we start with 10 stones, actually we're gonna get 10 times 33 million or something like that. So it's gonna, the number of starting stones times 2 to the 25th, which is a big number. It's not gonna be that number, it's gonna get lower because we do have two rules that basically keep the number of stones, only change the numbers, but it is what it is. So let's get started. The input is just an array of numbers, just a list of numbers. So we will take that into account. So instead of a string array, we're just gonna have a number array. We're just gonna read the input as a single line. So this is a string. And then we're just gonna split that line on spaces, because the demo input is just this. We're gonna split on a space and map all the items, parsing them to numbers, or call them stones. We're gonna return the stones, and that's it. So we're getting a stone array, and actually I will leave this as input, but then I will do this. Input dot slice. I will make a copy of the input. So I want to make sure that I'm not destroying the input. And let's just run a for loop for 1 to 6, let's say, because that's the initial example. 1 blink, 2 blinks, 3 blinks, 4 blinks, 5 blinks, 6 blinks. Or this will be the loop that we're on. Let's do it properly. we're counting from 1, 2, 3, 4, 5, 6. And now we're gonna need to loop through the stones, but I think a for loop will be nicer because we're gonna play around with the indexes, so maybe we want to loop using a while loop. We're gonna start at 0 and we're gonna say while index is less than the length of stones. If index becomes equal to the length of stones, we're gonna do something like something. So we're just gonna say take the current stone, we don't need the next stone. If stone is 0, so we have literally just 3 rules. If stone is 0, then we need to increase the index, of course. We're gonna do that anyway. Which means it's not gonna be a constant, it's definitely gonna be a variable. So if the stone is 0, then we change it with a 1. Otherwise, actually I'm gonna implement this in this way. So if the stone is 0, then we do everything we need to do and we continue on to the next stone. Otherwise, I will take this, we need to count the digits. Let's do, there are some mathematical ways where you can count the digits, but let's do it this way. We're gonna take the stone, make it into a string, and get the length. Assuming that we're working with just numbers. JavaScript is kind of weird, so if we get some e's inside our text, we might be doing weird things. So 1, 2, 3, 4, 5, dot to string. This should work. Oh, we need to do it this way, so it's a number. Yeah, this is JavaScript thingy because it's actually reading it like this. If we add some more numbers, then you can see that we're starting to lose precision, and at a certain point it becomes in scientific notation. So once more, we're gonna need to take care that we don't run afoul of this value. But on the other hand, this value is quite large. Let's see if we actually have that problem. So we're gonna take the length of the string, and if that is even, then we're not gonna need to split this thing. Yeah, we're gonna do this way. Stone string dot length. We don't need to do that, we can just use the property. Then we're gonna need to get the halves. We're just gonna slice it, and this is a string, and we're gonna need to turn it into a number. And of course, we're gonna need to have the second half. I think this will work nicely, but if we have the second half, then we are setting the current value to the first half, and I think that we're gonna add another stone here at position index plus 1, which is the second half. And note that now we will need to increase the index by 2, because if we're on the third position, if our index is 3, now on position 3 and position 4, we already have know what we have. So we need to move to position 5 for the next stone. And that's one of the reasons why I wanted to do everything in this thing. Otherwise, if we don't have the rule number 1 and rule number 2, we have rule number 3, which means stone of index is not that fantasy, but is stone of index times 2024. And of course, we're going to increase the index. So let's write out the stones after each run of the loop. And otherwise we will need to return the number of the stones. So stones.length. Let's see what this thing does. So this is literally the first initial idea of what's going on, and we will mostly use it to investigate. So we have 223,000, 1 and 7, yep. So on the second loop we have 253, yes, 0, yes, 2024, yes, 14, yeah. After the sixth blink we have 22 stones, and first is a large number, then that one, and it ends with 76032. Yeah, seems like this is working. Let's run it for, let's move this out of the way and run it for 25 blinks. Oh. Let's actually get that over here so we can be more proper. Let's see what happens and how fast will this be. It says it's relatively fast and we have 55,312 stones. Great. That is the correct value. We were supposed to get 55,312. But let's go back to our proper input. So this has a bit more numbers. 1, 2, 3, 7 of them. 1, 2, 3, 4. Yeah, 8 of them. So it will be maybe more. 229,043. I really hope that we're not running afoul of max safe integer, and we're not. This was the correct number. We got a star. That's great. And let's see. Oh, we're not doing 50 millions. We're doing 75. Let's go back. So we're gonna need to basically do the same thing, the exact same thing, only the loop target is 75. As always, let's go to the small input and let's see how far and how we get along. I will just print the number of stones because I have a feeling this thing will grow and grow and grow and grow. And as you can see, we got lucky. It was by design, I think, that this thing actually starts increasing rapidly. Not rapidly, it's by a factor of 1/2 or something like that, but it starts to get unmanageable around loop 20, after loop 25. So we're gonna need to wait a bit to get the answer for loop 75. We will need a better solution. Why is this slowdown happening? You can see that between loop 29 and loop 30, it's basically much slower, and it's gonna get slower and slower and slower. It's because of the date structure we have. This is because of the array that we are using. Because what happens here when we splice a number? This is fine, we're just going to a certain position and changing that value. But splice is quite fast, but it does involve moving all the numbers that we have in the array one place over. So when we say we want to put something between third and the fourth place, and the array has 5 items or something like that, that means we are putting something new at index. So we're keeping the thing at index 2. We are creating a new value for the index 3. The previous index 3 goes to index 4. The index 4 goes to index 5, and so on and so forth. For 5 items, it works great. For 500,000 items, not so great when we move the second one. So that means that each and every time that we do a splice, we need to create a new operation when we are moving things. Let's try to optimize this a bit. So let's limit this to 29 for now. Let's see if this is faster. So for 29, it took 5.5 seconds. Let's see what happens if we don't actually do this, if we create a new array. So I will use, we will just say that this is a variable thing. So instead of changing the stones, I will just say initially, let new stones, this can be a constant, is a new array. And now we're just gonna push items in. So new stones dot push 1. New stones dot push first half and push the second half. None of these splice things. And new stones dot push these things. So we're running the while, and after we're done, we're just say, well, the stones are the new stones. Let's see if this will use a bit more memory, since we have 2 arrays at any given time, but let's see if it's faster or not. It is a bit faster, but very, very, very incorrect. We're supposed to get 3, 4, 5, 9. 3, 4, we are getting 3, 4, 5, 6. So we have an error somewhere. Let's print out the stones. Missing something. So the first line is correct, the second one 253 is 0, and then we don't have a 2024. We missed a push somewhere, I guess. This index now stays increased by just 1. Because we're not doing on the same array, we're just literally taking it stone by stone. Let's see what happens now. Ooh, we got a huge thingy. Let's not write out the stones, let's just write out the length. Yeah, this runs faster. Let's see if it can get up to 75 or not. We're just pushing, we're not changing the array. Oh, it's moving along, it's gotten to 36 without any problems, 38, but we can see that 38 is actually a 8-digit number. That's 12 million, that's 19 million, that's 30 million. So this will eventually maybe get to 75, but right now the splice has something that's called kind of quadratic complexity if we're using it in a loop, because as we're adding items we have to move the rest of the array. This one just adds to the back of the array, so it's kind of linear. With splice, if we have an array that's 2 times as large, we would waste 4 times as much time and memory. Just time. For this, it's gonna be linear. So if something is 100 million elements, it will take 100 more than an array of a million elements, but still it will take some time. And of course it will take a lot of memory. So we're gonna, assuming that we have a factor of 1.5, so we're looking at the final value of, we run out of memory on loop 43. Let's take a look at this. How it's gonna be. It's gonna be starting with 8 numbers, but we have 1.5 to the 75th power. And that's this many bytes. And now we can calculate that, multiply that by 8. So it's this many bytes. This is a megabyte. This is around a gigabyte. This is a terabyte. So we're gonna need something like 128 terabytes of memory to actually put all of this in memory. Seems like we're gonna need a different approach. But we're gonna take on that approach in part 2. Anyway, mash the buttons, click like, subscribe, and keep developing.